Welcome to Data Warehousing and Data Mining video lectures. I am Dr. Eswap Chintalpudi, working as Associate Professor in the Department of Computer Science Engineering, Pragati Engineering College. Today we are going to discuss about association analysis. As per the R16 syllabus, we are going to discuss association analysis and its basic concepts and its terminology and algorithms, and what is the problem statement, and frequent item set generation using a priori algorithm, and rule generation and compact representation of frequent item sets. Finally, we will discuss with the FP growth algorithm. Here in this syllabus, whatever we highlighted with red color, that is the topic of today. So in this class, we are going to learn about the basic terminology that is required to understand the association rule mining. Okay, and later on, after discussing about the basic terminology, we get into the actual problem definition. Then we learn about what are the problems we are facing in association rule mining and how to solve those problems using a priori algorithm. Next, after completion of this particular chapter or this particular course, we attain a course outcome. The student will be able to compare a priori algorithm with FP growth association rule mining algorithm for frequent item set generation. Here in this chapter we will discuss both a priori algorithm and FP growth algorithm. So at the end of this particular chapter, the student can be able to compare the a priori algorithm and FP growth algorithm. Now let's get into the actual terminology of association rule mining. What is association rule mining? If you see the transaction databases where we see in the real-time world like DMart, Spencer's, like Reliance Trends, like that, all those marts will maintain a transactional database where we found a transaction ID and the list of items that bought together in a particular transaction. Okay, here given a set of transaction, we need to find the rules that will predict the occurrence of an item based on the occurrences of other items in the transaction. For example, we take the standard example that is prescribed in the Vipin Kumar textbook. That is, we see the transaction ID, the items, where we have 5 transactions and each transaction consists of set of items. Here the first transaction consists of 2 items, bread and milk. Like this we have 5 transactions. This is the standard example that is taken from the Vipin Kumar textbook. So what is association rule? So see, these are the 3 examples of association rules. The first one, diaper implied by B. That means diaper tends to B. What this indicates? It is in the form of X tends to Y. Okay? If the customer purchases the product X, there is a chance to purchase Y also. That is called association between these 2 products. Like this we have 3 examples here. Diaper tends to B, and next milk, bread tends to egg, coke. That means here the customers who have purchased milk, bread together, there is a chance to purchase eggs and coke together. And next one, beer and bread. The customer who purchases beer and bread together, there is a chance to purchase milk also. Okay, these are the 3 association rules here. These are the rules we need to produce by using association rule mining. This is the input. What is the input here? We are giving the transactional database as an input. We are generating the association rules. Here, important note about the association rules is implication means co-occurrence, not casualty. Here the thing is diaper, the customer who purchases the diaper also purchases beer. Here we are saying that. Here this is the implication. That means that indicates that co-occurrence. That indicates the co-occurrence. That is not the casualty. What is meant by casualty then? Because of the event X happened, the Y is happened. This is not the cause. Because of the customer purchasing the diaper, we are not having he is not purchasing beer also. Okay, this is not a casualty. Clear? Now we will discuss about the basic terminology that is required to understand the association rule mining. The first concept is item set. What is an item set? Item set is nothing but collection of one or more items. Collection of one or more items. As we see on the right hand side of the slide here, this is the transaction database we use throughout this chapter. Okay, where what we have two columns here, two fields, transaction ID and items. Here one represents transaction ID, bread and milk represents the items purchased in that transaction. So bread and milk together we can call it as a item set because we have two items in it. So a collection of one or more items is nothing but item set. For example, milk, bread, diaper. Next, if the item set consists of only one item in it, then we can say that one item set. If the item set consists of two items in it, then we can say that two item set. Then generally we can say that if the item set consists of k items, then we can say that that item set is called as k item set. So we will use this notation in the algorithm. A k item set consists of k items. Next, that is a fundamental concept of association rule mining, item set. Next, we will discuss about support count. Support count will be represented by the symbol sigma. Here this indicates that the frequency of occurrence of an item set. Frequency of occurrence of an item set. For example, sigma of milk, comma, bread, comma, diaper is equals to 2. This indicates that in the transactional database, milk, bread, diaper together appeared in two transactions. Please observe this database. In the database, we are having 5 transactions. These five transactions, milk, bread, and diaper appeared 2 times. That means the 2 transactions. That is 4th transaction and 5th transaction. That's why sigma of milk, bread, diaper is equals to 2. The frequency of occurrence of milk, bread, diaper is 2. This is called support count of milk, bread, diaper. Now we will get into the next concept, next terminology, support. Here support is nothing but the fraction of transactions that contain an item set. The fraction of transactions that contain an item set. For example, for the same set of item set, S of milk, comma, bread, comma, diaper is equals to 2 by 5, where 2 represents the frequency and 5 represents the total number of transactions in the transaction database. 2 by 5 represents the support of that particular item set. Next, we will discuss about frequent item set. What is frequent item set? Normally, literally, the meaning of frequent item set is nothing but the item set which is repeated so many times in the transaction database. Okay. So here what we use is, first we need to find out the support. If the support of the item set is greater than or equals to minimum support, then we can say that that item set is called as frequent item set. Okay, these are the basic terminology that are required to understand association rule mining. The first one is item set, second one is support count, third one is support, fourth one is frequent item set. Now we will discuss what is association rule. Any rule which is in the form of extends to y is called as association rule. Any rule which is in the form of extends to y is called as association rule, where x is an item set, y is also an item set. No need to be y is a single item. Okay, sometimes we may have x may be a set of items, y may be a set of items. Clear? For example, milk, comma, diaper tends to be. What this association rule represents? If you observe this association rule, what this indicates is, if the customer purchases milk, comma, diaper together, there is a chance to purchase beer also with the transaction. Okay, and next one. Okay, once we generate the association rules here, how to evaluate these rules? We have two metrics, those are called as support and confidence. Support will be represented by S, confidence will be represented by C. Support is nothing but fraction of transaction that contain both X and Y, which is we discussed in the previous slide. And next one, confidence. The confidence is represented by C, and which indicates that measures how often items in Y appear in transactions that contain X. So here where support indicates that the fraction of transactions these items together, that will be discussed in, that will be measured in support. Whereas confidence here, this is a relationship between the X and Y. In how many transactions Y is appeared where X is there. Okay, that will be determined by the confidence. See the example. Here the association rule is milk diaper tends to B. First we calculate the support. Support is equals to sigma of milk comma diaper comma B by total number of transactions. In how many transactions milk diaper B appear in the database? There are two transactions, 4 and 5. That's why I am mentioning here 2. How many number of transactions are there? Total we have 5 transactions. That's why 2 by 5. 2 by 5 equals to 0.4. This indicates the support value of this association rule. Next, we compute confidence. Confidence is nothing but sigma of milk comma diaper comma B by sigma of milk comma diaper. This represents that, as we already discussed, that support of milk comma diaper B is equals to 2. That means here, in how many transactions milk, diaper and B appear? In how many transactions milk, diaper, bread, bean appear? 2 transactions. Okay. So next, in how many transactions milk diaper appeared? Milk diaper is appeared in 3 transactions. 1, 2, 3. Okay, 2 by 3. That is equals to 0.67. For this association rule, we are having 40% support and 67% confidence. Okay, clear? Next, we will get into the what is actual association rule mining task. The problem statement is they will provide a set of transactions. We need to mine some of the association rules, which will have the support should be greater than or equals to minimum support, confidence should be greater than or equals to minimum confidence. Okay, this is our problem statement. This is the actual association rule mining task. And the first initial approach is brute force approach. In this approach, what we do is we will list all possible association rules by using the item sets. Then we compute support and confidence for each and every rule, and then prune the rules that fail the minimum support and minimum confidence threshold. Okay, so what we do in this approach, initially we will list all possible association rules and then compute support and confidence for each rule, and then we prove some of the rules based on the minimum support and minimum confidence threshold. If the minimum support is, if the support of an association rule is less than the minimum support, we eliminate such rules. If the confidence of an association rule is less than the minimum confidence, then we eliminate such association rules here. But if you observe, this approach is computationally prohibitive. That means computationally expensive. Okay, that's why it is computationally expensive means here we will look into an example and observations of it. So this is a given database, transaction database. We have taken all the above rules are binary partitions of the same item set, milk, diaper, bean. I am taking 3 items, milk, diaper and bean. By using these 3 items, I have listed out all the possible association rules. Okay, these are the possible association rules which comprises only 3 products, 3 items, milk, diaper and bean. Okay, milk diaper tends to bean, milk bean tends to diaper, diaper B tends to milk, B tends to milk diaper, diaper tends to milk B, and milk tends to diaper and B. These are the set of transactions, the set of rules that are produced from the milk diaper B. Here, what we have is, we have computed for each rule as per the brute force approach. We need to compute support and confidence for each and every rule. So we have computed support and confidence for each and every rule. If you observe that support of all these rules is same, 0.4. That indicates that the rules originating, this is the observation we found in this problem, rules originating from the same item set have identical support. What we have? Identical support, but can have different contents. Contents may be different, but support will be same with the same items. Thus, we may decouple the support and confidence requirement. So, what we can do is, by this problem, what we can suggest is, we can decouple support measure and confidence measure. Whereas they are combining support and confidence measure in brute force approach, in the later on, what we do is, we separate support and confidence. We separately calculate support and separately calculate confidence. So now, what is the actual approach of mining association rules? There are two steps. This is a two-step approach. In the first step, what we do is, we will find out the frequent item sets. Frequent item set. In the second step, we will generate the actual association rules. In the first step, what we do is, we generate frequent item set. What is meant by frequent item set? An item set, if we calculate a support, if the support of an item set is greater than or equals to minimum support, then we can say that, that item set is frequent item set. We generate such item sets in the first step. And now let's see the generic algorithm for mining association rules. This is a two-step approach where the first step is frequent item set generation, the second step is rule generation. In frequent item set generation, what we do is, we generate a frequent item set. What is meant by frequent item set? If we compute support for a support for item set, if it is greater than or equals to minimum support, then we can say that that item set is a frequent item set. We generate such frequent item sets in this phase. In the second step, what we do is, we generate association rules, where we need to generate high confidence rules from each frequent item set, where each rule is binary partitioning of a frequent item set. For example, what we discussed in the previous slide is, we decouple the support and confidence. Okay, in the first step we use support. Here, in the second step, we use confidence. In the first step, we compute the support. Based on that, we can compute what are the frequent item set. In the second step, we will compute confidence for each association rule for binary partitioning of a item set. Now we compute confidence for each association rule, then we pick up only high confidence association rules. Clear? Now, this is a two-step approach for mining association rules. Frequent item set generation is still computationally expensive. Why? Because we have a lot of item sets in transactional database. To compute support for all the item sets, it will take more time. So that's why it is computationally expensive. So we see how it is computationally expensive. Let us take an example. In this example, we have 5 items called A, B, C, D, E, and if we construct a lattice to obtain all the possible candidate item sets, then this will be the resultant structure. For example, if we are having A, this is a 1 item set, where AB is the 2 item set, ABC is the 3 item set, ABCD is the 4 item set, ABCD is the 5 item set. Because we are having only 5 items in this example. So see this, here we are having only 5 items. If we have 5 items, these many possible candidate item sets we have. Is it computationally expensive or not? Why? Because frequent item set generation. Now we will see why frequent item set generation is a computationally expensive task. See this, in this example, we are having 5 item set. 5 items. For these 5 items, these many possible candidate item sets we got. This is a lattice structure where we construct for all the possible candidate item sets. For example, if I take D items, there will be a 2 power of D possible candidate item sets. The 2 power of D is an exponential number. 2 power of 1. For example, it is a 5 items, that means here 2 power of 5. 32 number of candidate item sets we may get for 5 items. For 5 items we are getting 32 number of candidate item sets. Okay. So in the real time world, are we having only 5 item sets? No. In the real time world we have millions of products. Okay, in such time, what will happen here? 2 power of n is very computationally expensive. That's why. So we need a solution for this. So anyway, what we need to do is we need to cut short the number of possible candidate items. This is the one possible solution we have. See this, in the brute force approach, what we do is each item set in the lattice is a candidate frequent item set. Count the support of each and every candidate by scanning the database. Each and every time we need to scan the database. Whenever we want to compute support, what we need to do is we need to scan the entire database. Here consider this is a transactional database where n represents the number of transactions, w represents the average transaction width. Transaction width is nothing but number of items in a item set, in a transaction. So average transaction width will be represented by W. For milk and bread, we are having several list of candidates. That list will be represented by M. M is the list of candidates. As we already seen in the last slide here, if we have D items, then how many number of candidate items we can get here? 2 power of D. That means if we have, so that means here, if M value is 2 power of D, then if you find out the complexity of this particular algorithm, order of n into m into w. So where m will be the exponential number, then the time complexity would be a exponential. Exponential time complexity is the worst time complexity for any algorithm. So we'll see what are the possible solution for this problem. The first one, either we need to reduce the number of candidates and next reduce the number of transactions, or we need to reduce the number of comparisons. Okay, first we see reduce the number of candidates can be done by a complete set m is equals to 2 power of d. We use some pruning techniques to reduce m. That means we'll use in later on we use some pruning techniques by using support. We can reduce the m. If you reduce the m, what will happen here? The time complexity of the algorithm will be get reduces. The same thing, reduce the number of transactions. Number of transactions means here, what will happen here? If the number of transactions increases, the complexity of the algorithm will also be increases. So either we use DHP and vertical based mining algorithm, they are the two different algorithms, or to reduce the number of transactions. We eliminate the duplicate transactions, that's it. And next one, reduce the number of comparisons. N and M. So by using efficient data structures, so we can store the candidates or transactions in efficient manner. If you store the efficient manner, the search time, the number of comparisons will be reduces. If the number of comparisons will be reduces, the time complexity will be reduces. Okay, no need to match every candidate against every transaction. Okay, we'll skip some of the candidates based on some efficient data structures. The possibilities are, so we prefer the possibility of reducing the number of candidates. So now we have a principle to reducing the number of candidates. The principle is that if the item set is frequent, then all of its subsets must also be frequent. Converse of this is, if an item set is infrequent, then all of its supersets are also infrequent. Clear? Now, so how we derive this principle? Based on a priori principle holds due to the following property of the support measure. For all x comma y, x is a subset of y, tends to support of x always be greater than or equals to support of y. What this indicates? Support of an item set never exceeds the support of its subset. Support of an item set never exceeds the support of its subset. That means here subsets will have the more support than the supersets. Okay, always support of an item set never exceeds the support of subset. So this property is called as anti-monotone property. Okay, based on this property, we can generalize this. We can generalize the item set frequency. If an item set is frequent, then all of its subsets must also be frequent. The converse of this principle is that if an item set is infrequent, then what we do is all of its supersets are also infrequent. So if I found that if an item set is infrequent, then what I will do?